I didn't know that it's foldable or what. Suddenly it's significantly smaller in size, right? In height, the table, right? You remember it was up here, I guess, right? So now, okay, you can go up here. Okay. And another progress. Instead of paper clip, now there is this fancier clip. My own, right? So, as I keep saying, you have to come to the class with your own stuff. It's bizarre. I think paperclip was better.
Miks tegid ka? No mida teha, kui see silmas ennast parandaks? Nii tegid paberid ja jahipadi just ha. Ma tean ju milleks eksepti.
Okay, so it looks like based on the number of students, you scared more about the final exam. Because as I told you from the very beginning, chapter 12 will be significantly more complicated because lots of things are far from being intuitive. Right? It takes time to get used to this one. But then, as usual, seven problems, right? First multiple choice, and then there will be 6 big problems, right? From different parts of the class. But again, at least close to 70% of the exam, between 60 and 70, will be based on the new material, basically, which we covered after the third exam, right? Which will be based on chapter 12, right? Torques, angular momentum, conservation of angular momentum, rotational Newton's second law, and stuff like that, right? So at least 60 or 70% will be based on that. And then maybe 2.5 or maybe 3 problems will be about the previous material. And again, all the time, I emphasize on the major points, right? On big points. So what else? Any questions about the format? I feel like something want to say something else. I don't know. Okay, it will be a long evening, so long night, so we can talk about everything. So as usual, first I will review the major ideas, the major formulas which we need for the exam, and then problems. Again, as usual, it's you can come and go, right? Feel free, you can move yourself, right? No problems, right? You can stop me at any moment of time and ask any questions, right? All kind of ridiculous questions, right? Anything. Right? All right. So let's start. Felix, there's a strong feeling that I missed something. Right? I don't know what. Okay. So we started at the very beginning introducing a few random things, basically preparing ourselves for full rotational dynamics. So we introduced center of mass, moment of inertia, stuff like this. So let me write that down. So first section will be, let's start with center of mass. Center of mass. Right, and we introduce it, okay, I will write it in a vector form. So RCM, it's you take mass, multiply by the position vector which defines its position, then second mass the same, third mass, all these products and add them up, and then divide it by the total mass of the system. M2R2, and plus so on, and divided by the total mass of the system. And of course, you can easily write it in a component form, right? So just replace all these r's with x1, x2, y1, y2, and you can write, you can calculate components of the center of mass. Okay, then we introduced rotational kinetic energy. Okay, so which symbol we use? K. K rotational. 1/2 I moment of inertia omega squared. Right. Okay, Okay, let me frame it because it's a important part. And that's where first time we saw new quantity moment of inertia. It's a rotational equivalent of mass. So now in order to describe inertia of a system during the rotational, in the rotation, information about the mass is not enough. You also need to know how that mass is distributed relative to the axis of rotation. Right, so now it's time to introduce formulas for the moment of inertia. I, moment of inertia. Again, if something not clear about my handwriting, just tell something immediately, right? So I can clarify. Okay, so first, for a point mass, let's say this is our axis of rotation, right? And let's say mass is over here. So now, in order to find moment of inertia, we need to know the shortest distance, perpendicular distance, from the mass to the axis of rotation. So every time we have different r's and different meaning of all those r's. So you need to be, you need to understand the meaning of each of those r's. So in this case, you need to know these r. So for point mass, in this case, moment of inertia is mr squared. Moment of inertia is additive. If you have two masses, mr squared plus and so on. Right? So that's for point mass. For a single particle, let me write on top. Single particle. And, okay, it's the first, and then for a rigid object, how do we usually find the center of mass of a rigid object? We just open the book, right? And I get it from table 12.2, right? But on the exam, of course, I will give you formulas. If they are needed, I will give you a formula or the number. What's the value of moment of inertia? Because that's calculus 3, how to calculate these things. Okay, will be given. All right. Then, so this bullet, this moment of inertia, and now what's next? Vector product. Let's just quickly say a few words about the vector product. Because now we need it from time to time. So if you have, for example, two vectors, let's say this is vector A, this is vector B, right? And let me ask you, is this the correct angle between these two vectors?
No.
Yes. You need to position tails of both vectors at the same point, right? In order to find the correct angle. So that is the correct angle. I like giving questions like this. Try to, yeah, right. Okay, so A cross B. So absolute value. It's a magnitude of A, magnitude of B, and times sine of correct angle between them. So that's the absolute value. And direction, right-hand rule. Number one, that's what I call, right? Because we have two right-hand rules all the time. And in physics too, it will be exactly the same story. So right-hand rule number one, right? First, align your hand along the first vector, then orient it in such a way so that you can bend naturally your fingers towards the second vector, and as a result, your outstretched thumb gives you a direction of the cross product. All right, then we introduce these notations. If a vector shown like this, it means that the vector points into the board, right, into the screen. So this is in the board, into the board. And of course, if you have just a dot with a circle, it's out of the board. It's like an arrow flying towards you or away from you. Okay, so outward. Okay, so that's the first part. But you know, I feel like I'm spending too much space. Not wasting, spending, using. Now, second section. Now, after these preliminary steps, we actually started introducing rotational dynamics. And we introduced first the idea of torque. And we introduce it. It's basically by definition. By definition, torque equals, it's a vector, it's a R cross F. By definition. Right. So in order to describe rotational motion, we need this quantity. Information about the force now is not enough. We also need to know where that force is applied and at which angle that force is applied. And very important, I keep emphasizing on this. If I just ask you, what's the not moment of inertia, what's the torque, for example, acting on this camera, right? What should I add? Relative to which point, right, the torque is measured, right? So I cannot just ask in general, what's the value of torque? You need to specify relative to which point, right? Because of this R, torque, the same as angular momentum, are sensitive to the position of origin or axis of rotation if we're dealing with that. Okay, now let me remind all possible ways which we can use to calculate the absolute value of the torque. Okay, we already talked about this a few times. Let's say we have this fancy object, rigid object. And let's say this is my axis of rotation, and I can position origin, of course, at that point. And let's assume that I apply force, for example, over here. So force F. Then what is R? Of course, it's a position vector, defines position of the point where the force is applied. So that is our R. Okay, and now all ways which can be used to calculate torque. So first one, just straightforward, right? So torque equals RF and the correct angle between them. But this can be sometimes tedious. Diving into this angle business can be something not clear. Tau equals RF sine theta. Right? Okay, but we can use some shortcuts, which are useful sometimes. You can look at the picture and you can see those values. So, which are shortcuts? You can use something like this. F perpendicular times full R. So what does it mean? If I draw this line which goes through R, right, this line, F perpendicular, it's just a perpendicular component of this force, perpendicular relative to that line which goes through R. Okay, so it will be this. So this will be my F perpendicular. Right. Again, in lecture 20 we showed that, and I proved that. Now I'm just reminding you. Sometimes it's very useful. You just look at you can look at the picture and you can see the value of F perpendicular immediately. So you can use component of the force times the full R. Okay, now in the last trick which can be used, torque equals to R perpendicular times F. So now it's reverse. You look at the perpendicular component of the F, R, and the full F. So where is that R perpendicular in this case? What you do, you draw just a line of force, line which goes through the force. And R perpendicular is just component of this R, that component which is perpendicular. So this will be R perpendicular. It's especially in today's and tomorrow's recitation classes when you're going to balance some objects, these tricks can be useful. Okay, so let me frame this, because these are important. And exactly the same tricks can be used to calculate angular momentum, because the structure of the definitions are very similar. Here we have torque equals R cross F. In the angular momentum, R cross P. Right? So the same tricks can be used. Then, what's next? Okay, maybe I will write here. The same can be used to calculate, L, angular momentum. Okay, and now it's time to actually introduce angular momentum. Right. Is this the time? Yeah. Okay, so let me introduce now angular momentum. So, ang momentum. Okay, the definition, again, as I said, very similar, but now instead of F, we have linear momentum. Where did I write? Okay, for a point mass. For a point mass, L equals to R cross P. Okay, let me frame this, because that is the actual definition of the angular momentum. And again, if I ask you in general, what's the value of angular momentum of some object, question is not full, is not complete, because you need to know relative to which point you try to calculate the angular momentum. And for a rigid object, L equals moment of inertia times angular velocity. So what can you say about directions of angular momentum and angular velocity? They're the same all the time, because moment of inertia cannot be negative. It's only positive number, so as a result, L and omega are in the same direction. Then, what's next? Okay, now we have all ingredients, and now we can introduce the fundamental equation which can be used to describe any rotational motion in the universe. Rotational Newton's second law. Right? Rotational Newton's second law. Right, so let me separate this. And so let me move up here and introduce the fundamental equation, rotational Newton second law. Wow, you're really afraid of the final exam. Students keep coming and coming, right? Hello. Right. So the first form, the simplest form, but not the most general, torque acting on the object which has moment of inertia I leads to an angular acceleration alpha. Right? Sort of similar to F equals ma, but now instead of mass we have moment of inertia, instead of linear acceleration, angular acceleration, and instead of force, rotational equivalent of the force, which is torque. Right. And the most general form of the rotational Newton's second law, because this form cannot explain motions where moment of inertia changes with the motion. Right? So now we can introduce the most general form as torque equals to rate of change dl over dt. L is our angular momentum, right? Okay, so this is a general form of Newton's second law, of rotational Newton's second law. Sorry, rotational Newton second law. So okay, we're getting closer. We have 3 more boxes, and right. Then, yeah. Now we started applying this Newton's second law, rotational Newton's second law, and we ended up with conservation of angular momentum under certain conditions. So let me state that. Which way? So now, conservation of angular momentum. Again, if something not clear in terms of handwriting, tell me immediately. Right? Yeah. Conservation. K-O-N-C, right? S. C-O-N-S. It's 6 p.m. Right. Students from my recitation in the sections can tell you even weirder things which I was pronouncing today. All right.
Door, wall.
What?
Door was the wall.
Yeah. Come on. Don't review that. All right. Yeah, it's been a busy week. All right. Where I am. Yeah. So, if net external torque acting on the system is 0, in our cases, most of the time it's if friction force is missing, then angular momentum is conserved. Then we can write that L initial equals to L final, conservation of angular momentum, right? Right, and then today, yeah.
You said it would be 0 if there's no friction.
Say it again because of the doors.
You said it would be 0 if there's no friction.
Okay, it depends on the situations, but most of the situations which we had so far with conservation of angular momentum, it was about friction. If friction was missing, then external torque is 0, and as a result, angular momentum is conserved. But I will never ask you to justify conservation of angular momentum because it's much more complicated, right? Not that complicated, but if, for example, question the problem asks you, what is conserved in the problem? Because it's a clear indication that you will have to use conservation of something, right? And if you see that there is a rotational motion, it's a clear indication it's an angular momentum. Because linear momentum you cannot introduce for a rotating object. And energy, conservation of mechanical energy, it's, yeah, we'll give you a hint, right, or something, right? That conservation of mechanical energy can be used, right? So if there's a rotational motion, most of the time it's a conservation of angular momentum. Okay, so now let me separate this and static equilibrium, today's stuff. Static equilibrium. Static equilibrium. So basically, we introduce conditions under which you can prevent any types of motion. If you don't want to have rotational motion, translational motion first, you need to demand that some of the forces in the x direction, they balance each other out. It guarantees that you're not going to have any translational motion in the x direction. Then, if you demand these, some of the forces in the y direction, they balance each other out. It guarantees that you're not going to have any translational motion in the y direction. And we're going to restrict ourselves all the time for two-dimensional situations. All forces will act in the xy plane. And as a result, the third condition, okay, let me put number 1, number 2, and number 3. Torque can be, in this case, only in a z direction. So if net torque in the z direction equals 0, it will prevent, it helps you to avoid any rotational motion, right? Again, what do I have to add to this condition? Very important part, crucial part. Information about the axis. Because torque, value of torque. Depends on where your axis of rotation is, right? And we showed in the class today that we have a freedom to choose any axis of rotation, right? Okay, we have a freedom. And I need to mention that, okay, over here, the choice of an axis is arbitrary. The choice of an axis is arbitrary. So basically you can pick any axis of rotation. Okay, we discussed that in the morning, and right, so it's time to separate this part and the last. Yeah.
The small subscript below 4 for number 3.
X, Y, Z. Okay, and the last part. If you have a rigid object like this, how can we find gravitational potential energy? We can use the beauty of which point? Center of mass, right? Find the position of find the center of mass point, create a fake particle with the total mass of your object, position it at the center of mass, and then calculate the potential energy of that fake particle, right? It's one of the beauties of the center of mass point. It has plenty of beauties. It simplifies our life in physics and engineering tremendously, the center of mass, right? Okay. So, gravitational potential energy. Gravitational potential energy of a rigid object. Rigid object. Right, so let's imagine that we have some arbitrary shape rigid object. Let's assume that this is our reference level. U gravitational equals 0. So let's assume that this is our center of mass, Cm. Right? So what you need to know this distance, which we can call, which we label yCm. Y sub Cm. Right? And so as a result, gravitational potential energy, U gravitational will be mg y Cm. Right? Again, we assume that the total mass of the body is m. Okay, so these are, okay, let me separate this. Major points after we had our third midterm exam. So basically, like as I said, about 60–70% of the exam will be based on these ideas. Okay, any questions? Or so far, comments here?
So for multiple choice, can we assume that most of the multiple choice will be centered around this?
Okay, I cannot guarantee that. That's, I just look at the big problems, right, in order to complement them, right, so avoid overlapping, I pick some multiple choice questions. Lots of questions come from the clicker questions. Right? Okay. Anything else? Yeah.
Like, under what circumstances will the external net or the zero?
Under which circumstances? Occasionally it happens, so more than occasionally, right? If I, we're going to look at the examples, right? And we already had, like today, I was spinning, right? Putting myself in danger, right? Where was the friction force? Which we neglected. It's that there is a bearing right between the top part of the turning chair, right? So since we have a nice turning chair, right? So between the foundation of the chair and the top of the chair, almost there is no friction. Okay, small one. We can neglect it. So if we had significant friction over there, angular momentum would not be considered, right? will dump all our angular momentum, right, in trash. Okay, anything else? Wow. Big crowd. Okay, so now let's start looking at the examples.
Ja kindlaks tegid ka, no mida teha, kui see silmas ennast parandaks. Nii tegid paberid ja jahipaadi ostsid ma tean ju milleks.
You know what? Let's start with the cross product, vector product. A couple of examples about that. So what if you have, let's say we want to find a cross product between these two vectors, A and B, right? And let's say this is vector A and this is vector B. I'm just making it up. I have no idea. What's the direction of the cross product? First of all, you need to remember that the cross product is must be perpendicular to both of these vectors. Both of these vectors, they lie in this plane, so the cross product can be either out of the board or into the board. Right? And now let's just quickly apply right-hand rule. So first, you need to take first vector in the cross product, position your hand. Okay, again, I'm getting into the same weird situation, right? My students know what I'm talking about from the recitation classes. Okay, first you need to align your hand along the first vector. Okay, you got it, right? So, okay, all right, along the first vector A. Then you need to orient it in such a way so that you can bend your fingers naturally towards the second vector. So second vector, this way. And my outstretched thumb gives me direction outward. Or like my professors, when I was in your shoes, right, first, second year student, right, they did this trick. Some people find it useful, let me just tell you. They would just grab second vector in the cross product and position it at the tail of the first one to create this unique flow. And then just curl your fingers in that direction, and your outstretched thumb gives you the direction. That's what I do all the time in my head. I just grab the second vector mentally in the cross product second, move it here to create this unique flow, and just curl my fingers. Yeah?
So there are two different rules.
No, it's the same rule. It's just the potato.
Yeah, we use either one.
Right? Huh?
We use either one for the same number.
Yeah, you can use three fingers, right? I explained to you why I don't like the three fingers, because it looks funny, right? Okay. Okay, let me give you a couple of more examples. So in this case, what did I say? Out of the board, right? Out of the board. So which is out of the board? Dot. C is a dot. Okay, so now a couple of more. So let's say we have vector B and vector A. What are the two possible directions? Again, C vector must be perpendicular to both of these vectors. Vector A is towards you, B is up. So they form this plane. So vector C can be either this way or that way. Right? So now let's just apply quickly right-hand rule to get the correct direction. So first vector, I have to position my hand towards you, right? And then I need to orient my hand this way. No, you need to turn yourself because you, yeah. All right, so A cross B, C vector is that way. So C is this way. Okay, now, one more example. Let's say vector B and vector A. Again, I'm just making it up. I have no idea. What's the direction? Up? Okay, it's possible, right? So it can be either up or down, right? Because again, these two vectors form this plane. So C must be either up or down. Okay, let me just quickly check. A that way, Then B is into the board, so I have to orient my hand like this, so I can bend my fingers towards the second vector B. You see B cross, it means into the board. So, did you say down? Yeah, so it is down. So C is down. Okay, it's quite possible that there will be situations on the exam where you'll have to find the direction of the cross product, right? It's still possible to survive physics 1 without knowing how to find direction, but physics 2, after somewhere mid of the semester, almost all the formulas will be about the cross product. So you will sooner or later you'll have to learn that. Right. Okay, any questions? All right, practice. If still struggle, you can come to me. Right, it's very mechanical, right? It's just a rule which you just need to remember. Wait. All right. Okay. Need more examples? Yeah, it's very close to you, right? Okay. Now let's what? What are you laughing about? Right. Okay, so now let's start with a moment of inertia. Again, some troubles. Some students have troubles with that. Right. Okay. Let's imagine that we have this system. So it's about moment of inertia. So we have rigid rod, right, of mass m. Then we have here the center of mass, Cm, and just above the center of mass we have a small point mass, m. And over here symmetrically another point mass, m. And these two masses are connected by a massless rod. Oops, slightly off. This rod is massless. Massless. Okay, and again, if I ask you, for example, what's the moment of inertia of this system? What should be your response? Like people who already know physics. Where is the axis of rotation, right? Moment of inertia, it's sensitive, right? So if you try to spin it around this center of mass point, it will be one number. If you try to spin it relative to this axis of rotation, it will be different number. Moment of inertia is sensitive. So you just question what is the moment of inertia. It's not a complete question. So okay, so let's assume that our axis of rotation is here. So we're spinning it this way, so this is our axis. Let's say this angular velocity omega. Okay, and now let's calculate moment of inertia. Because almost every problem about rotational dynamics, in every problem you have to find sooner or later what's the moment of inertia. Because it's a crucial part. And moment of inertia is additive. Right? If your system consists of several parts, find moment of inertia of this part, that part, add them all up. Okay, done. And of course, all those numbers are positive all the time. Moment of inertia cannot be negative. Okay, so in this case, moment of inertia total, let me write it, equals moment of inertia over rod, which way I label it? Rod. Plus moment of inertia over point mass, plus moment of inertia over point mass. Since we have 2 point masses. Those massless rods, they're massless, right? They don't contribute anything. How can we find moment of inertia over rod? Table, right? Open the book, right? Or ask me on the exam if I don't give it, right? So from the table, I don't remember at the top of my head. Okay, so this is table 12.2. Right. And that moment of inertia is equals 1/3 m. Yeah, what else is given? The total length. This is L. Right. Okay. Times L squared. Right. Okay. Then, okay, I can write, so it's a 1/3 mL squared plus moment of inertia of a mass. The formula is mr squared, right? R is that shortest distance from the mass to the axis of rotation, perpendicular distance. Right? So what's that distance in our case? Half a L, right? 1/2 times L. Right? So it will be plus mL/2 squared. That's R over here. You see this R. And the second mass contributes exactly the same, right? So this distance is L/2 because they are just above and below the center of mass. So plus mL/2 squared. Okay? Basically everything comes from the geometry of the problem, of the situation. And, okay, I don't want to calculate this. No, I will have to. Right, okay, let me factor out L squared. So it will be m/3 plus m/4 n times 2. Because 2 exactly the same terms. So you can have, for example, let's say some turntable and 2-point masses near the edges. How can you find the moment of inertia? Let's assume axis of rotation goes through the center. Moment of inertia of a disk, then plus mr squared plus mr squared, right? If you have more masses, just keep adding, right, more and more terms. Just to remember, r, that small r in this case, it's the shortest distance, perpendicular distance from the axis of rotation to the mass, to the position of the mass. Right. Okay. Let me ask you this additional question. What's the direction of omega vector in this case? Positive. The pseudo vector. Positive is not enough. So what does it mean, positive?
It's going counterclockwise.
No, okay, I asked as a vector. You remember we introduced omega also as a vector. Okay, it's a pseudo vector, strange vector, weird vector, not typical. Lots of way of insulting it. All right. Right-hand rule number 2, right? Since it's spinning this way, right? So curl your fingers in the direction of rotation, and your outstretched thumb gives you direction of omega. So what's omega? Oh, yeah, of course. Omega is up, right? And then what's the direction of angular momentum, for example, of this system? Also up. Where is it? Here, I omega. If omega is up, L also up, right? Okay, right-hand rule number 2. Again, in physics 2, we're going to use the same rules. Again, to find the cross product, direction, and then to find, for example, direction of the magnetic field of some infinitely long straight wire. The same rules. Okay, so enough of warming up. All right, just simple problems now, real problems, right? Okay, any questions about this? No? Okay. Yes. Okay, still alive, but I will always... At some point I need to get a better camera. Okay, can I erase it? Actually, I started probably. Okay. You're not screaming, it means it's fine, right? You're not screaming, you're laughing all the time, right? I don't know which is better. So now, let's assume this situation. We have a stick on a frictionless surface, basically horizontal surface. All right, length L is given. Again, as usual, you remember we shoot the bullets here, right? So let's assume that bullet flies, collides with the stick at the midway point. And it doesn't get stuck, it flies through. So we'll know velocity before collision, after collision, right? And we will have to find angular velocity of the stick. Okay, let me draw this situation, write what is given. Right, so let me label this as a stick and a bullet problem. Stick plus a bullet. Right. Okay, I will start with the picture. So let's say this is my stick. The axle goes through the center of mass. Basically, this is the axis of rotation. A real physical axle goes through the center. So it's not some imaginary. Then, what is given? So about stick. So we have mass, which we label it M capital is 0.27 kilograms. Actually, it's quite light. Length of this stick is 1 meter. Then, and initial angular velocity? Zero, of course, right? Because it is at rest waiting for the bullet, right? So omega naught equals to 0, right? So then, bullet. Initial velocity, which we label it, I think, V1. Yeah, V1. Okay, so the bullet travels along this line of motion. This is the line of motion of the bullet. Right? Okay, so this is M, and initial velocity, V1. Right? V1 is 250 meters per second. Mass of the bullet is 3 grams, so which is 3 times 10 to the power minus 3 kilograms. Right. Okay. Then, its initial situation, let me label it as I, initial. Now, final situation, F over here, I will draw. So now the stick will start spinning with angular velocity omega, which we label it omega. Now let's label it final. And that's what we need to find. A bullet, it doesn't get stuck. It travels through, making a hole. Right, so here there is a hole. Okay, it's a line of motion. So making a hole, and bullet will continue traveling with velocity v2, and velocity v2 is 140, I think, meters per second, right? Yeah. Of course, we will need moment of inertia of a stick, right? And I will give it moment of inertia of the stick equals to 1 over 12, again, relative to the this axis of rotation, which goes through the center of mass, 1 over 12 mL squared. Okay, that's it. Nothing else. We need to find omega F final. Check. Yeah. What? Usually in the questions like this, I ask, so first of all, what is conserved in this situation? So, you know what? first of all, how many objects are there in the system? What is our system? Bullet and a stick, right? So if we talk about angular momentum of the system, it's angular momentum of the bullet plus angular momentum of the stick, right? And what is conserved? Angular momentum, rotational motion, right? It's a clear indication, more or less clear indication that we're talking about angular momentum, right? Which force can actually ruin this conservation of angular momentum? We assume it's a top view. For example, imagine that this stick lies on the icy surface, right? And the axle goes through the axis. Friction force. Friction force. If we had a friction, if you put this stick on this floor, there will be lots of friction and angular momentum wouldn't be conserved. Actually, what can be used if the angular momentum is not conserved? Like in the previous class, I said, okay, life is over, right? If linear momentum is not conserved, right? No, if angular momentum is not conserved, go back to the rotational Newton's second law and use just rotational Newton's second law, right? What a big deal. So angular momentum is conserved. We're going to use, again, I will write, so since net external torque equals 0, in this case, no friction. Right? So we can use L initial equals to L final, conservation of angular momentum. So, you know, before I start crunching these expressions, right, let me ask you this. Before collision, where is the whole angular momentum of the system? In which object? In the bullet, right? The bullet carries angular momentum, right? Stick doesn't have any angular momentum, it stays still, right? It's not spinning, right? Then, during the interaction, what happens? After the interaction, angular momentum will be both in the bullet and in the stick. So basically, during the interaction, angular momentum was shared. And now bullet basically shared angular momentum with the stick. Because of what? Which quantity helped to share this angular momentum? During the interaction, here there will be lots of forces between the bullet and the stick, right? Internal forces. Those internal forces give us internal torques, right? Which cannot change the total angular momentum, but within the system they can redistribute this angular momentum. So before, angular momentum was completely in the bullet. After the collision, angular momentum is in the stick plus something left in the bullet, right? So that's the role of internal torques. They help to redistribute angular momentum within the system. But they are not capable of changing total angular momentum. Right, okay, so now those just are philosophical discussions. Right now, let's go back to this, which we label, I think, with the upper script, yeah. Right, so before, L initial over bullet plus L initial over stick. M small, M capital. M small, it's a bullet, M capital is a stick. And then angular momentum final over bullet plus angular momentum of a stick, of this stick. Right, so what's the stick? It's a rigid object, right? So which formula can be used to find angular momentum of a rigid object? Where is it? I omega, right? I omega. So this, over here, this I can write it as I times omega. So what's the value of this angular momentum? 0, because the stick is at rest. Okay, let me dump this. This is 0 since that is 0. Okay, and now let's just calculate the rest of the terms. Let's start with this. That's where usually students have troubles calculating angular momentum over point mass. Lots of mistakes over here. So let's look at this. L initial over bullet. Okay. Right. So we have these tricks for torques, but exactly the same tricks can be used to calculate this angular momentum over point mass. Because you see the structure, R cross P, R cross F, exactly the same structure from the mathematical point of view. So you can use all these tricks also to calculate angular momentum over point mass, right? R perpendicular times P, or P perpendicular times R, right? So all those tricks can be used. Okay, so we can use R P sine of angle, or which trick, this or that can be, it's easier to use in this case. Which example, this or that? R perpendicular is easier to use, right? Because, okay, what is, this is also our P, right? Linear momentum, which is mv, right? So this is line of motion, and R perpendicular will be just this distance, right? So let me show it, this R perpendicular, right? Okay, and since this point is the midway point, let me remind you, it's a midway point, right? The total length is L, this is L over 2, and this will be L over 4, right? So this is L over 4. We practiced this rule in our recitation classes. You remember we had 2 point masses traveling, one is horizontally, one is vertically, right at the end of the recitation class, and we had to calculate the total angular momentum of those 2 point masses. So the same trick I applied here. Line of motion, so line which goes through the linear momentum, and then the shortest distance between the axis of rotation and the line of motion. Okay, let me use it. R perpendicular times P, right? So R perpendicular is L over 4, and P is mv1. It's a before, right? Initial velocity is 1, v1. So that's the angular momentum. Remember this trick. And the same can be used to calculate torques. We will get to torques maybe in half an hour or so. Right, so what's next? We can use the same to calculate this angular momentum of the bullet after the collision. So let me do this. So LFM. Again, I will use the same R perpendicular. Let me add subscript P1 because that's the linear momentum before the collision. And R perpendicular P2, exactly the same. Line of motion, axis of rotation still the same place, right? So now R perpendicular is still the same, L over 4. Right, so it will be L over 4 times mv2. Okay. And the last, so just moving these, now the last angular momentum over a stick after the collision, L final of a stick. So what can I write over there? Which formula? Angular momentum over a rigid object, I times omega, right? I times omega final, which we need to find actually, right? Yeah. So now let's plug them all in our conservation of angular momentum and see what we can get out of that. So first, L over 4. Okay, maybe I will show that I'm moving this. Whatever. So L over 4 mv1. It's this now that. L over 4 mv2. Then this I omega final. How many unknowns are there? Given omega final is unknown. Okay, one free and one unknown, right? So we can easily solve it for omega 2. I mean omega final, omega f. So it will be, this term goes to that side with minus. Right. And then I will divide the whole thing by moment of inertia. So it will be L over 4m v1 minus v2 and divided by moment of inertia. Just a little bit of algebra. Actually, here there are numbers. Wow, I'm surprised. I like crunching numbers. Okay, moment of inertia. Let me write it also. L m v1 minus v2. Since a moment of inertia is given, it's 1 over 12. So 4 1 over 12 m L squared. I just used expression for the moment of inertia. And 4 went from here to denominator. So 4 and 12, they cancel. L, 1L can be canceled, so we have m v1 minus v2 divided by, okay, 3 goes upstairs. After cancellation, 3, okay, in the denominator, right? Wait, numerator, sorry. So 3 and m L. Okay, so that's good. The simplest form of the answer, and now if you plug numbers, you will get 3.66. Wow, it's fast. 3 almost 0.7 radians per second. 1 radians is almost 60 degrees, 57 degrees. That's quite a speed, right? Okay, basically the problem is solved. Now I decided to add additional part. Okay, any questions about this? Again, the trickiest part, just a second, right? You need to remember this. Of course, you can go through the business of angle, right? So what is correct angle, use trig identities, right? And sooner or later you will get to this. But if you just remember it, you can use it, right? And of course I will buy when we grade these problems. So you can open any book and they all talk about this R perpendicular, F perpendicular, P perpendicular, and stuff like that. Yeah?
How do you know if you use 112 mL?
Okay, it's given.
Always.
Yeah, moment of inertia, it's a calculus 3 calculations of moment of inertia of rigid object. It's not trivial stuff. You need to be familiar with integration around over lines, surface, volume, right? So it's at some point you will learn that, right? Anything else? Okay, now additional question I added. So, what is kinetic energy of the stick after the collision, of course? Before it doesn't move, right? It doesn't spin, so there is no point of talking about any rotational kinetic energy. What do we have to do? Just grab the formula. Moment of inertia is given. Okay, let me first find the formula where that is somewhere over here at the very beginning. Moment of inertia is given 1 over 12, right? Then angular velocity we just found. Plug and calculate, right? So nothing special. So K rotational will be 1 over 2 I omega final squared. Again, this is, why did I say 1 over 12? It's 1 over 3, no, it's 1 over 12, sorry. And omega final squared. Okay, so here nothing to discuss, just find the right expression and plug and play. So you will get 0.15 units. It's just normal kinetic, it's just normal energy, right? Associated just with the rotational motion. Joules, right? Joules. Right. Don't forget about the units, of course, on the exam. Right? Again, I keep reminding you that most of the troubles are over here. Calculations of the angular momentum over point mass. Less troubles with a rigid object. Really, no comments? Nothing? Okay. The next problem I will skip, but you will see in your, I will send notes, right? It's basically conservation of angular momentum, but now you will have two rigid objects. It's even easier, right? So you don't have to deal with this R perpendicular P stuff or P perpendicular R stuff, right? It's just I omega, and I omega all the time, right? So I will skip the problem. Now, another lengthy problem. Yeah?
So the only reason why the external net torque is 0 is because there's no friction.
External, yeah. In this case, yes. So we assume that there is no friction between the axle and the rod, and also we assume that that surface underneath this rod stick is sort of like an icing, right? So those torques, yeah, I can actually justify, right? So if you don't believe me, right? So let's take, for example, this point, and when it starts spinning, what will be the direction of the friction force? If we assume that there is a friction force. It moves that way, spins that way, right? So the friction force will be this way, right? Then, so now let's calculate torque produced by this friction force. This is the axis of rotation. This is R, right? So take a cross product, R cross F. R cross F, it will be in the Z direction where our angular momentum is. So that's why all the time we keep dumping. But I didn't want to go into this business of showing the direction of the cross of this torque, right? But that's actual explanation. Because this torque produced by the friction force will be in this direction, in the direction where our angular momentum lives, right? But again, on the exam, don't try to explain this. Right? If you understand this, great, right? But at some point, of course, you'll realize it sooner or later. Anything else? Okay, now let's add complexity. All right, now the Atwood machine. Atwood machine. All right, so let's discuss this. Okay, so what is given? Now I need a big picture. This is my pulley. It's a pulley. So what is given for a pulley? Radius, R, mass, M capital. I think numbers, yeah, I have numbers. M equals 2. I can't imagine a pulley of 40 kilograms. What kind of pulley is that? Only when I started preparing the problem, it was so big. Right? Then radius is not given. Okay, less numbers. All right, then there are two masses hanging. So there is, of course, a rope which goes over the pulley. And so this will be my first mass. I think this is M1. Yeah, this is M1. Then there is a second mass over here, M2. So Atwood machine. Yeah, M1 and M2 are given. M1 is 6K, M2 is 2 kilograms. Cord is massless, the rope is massless, right? But pulley is not massless, so that stuff which we used a month ago here is not applicable, right? So we need to find acceleration of these masses. So we need to find acceleration. So in general, right, before we start applying anything, right, so what are we going to use? How many types of motions do we have here? Obviously 2, right? Translational motion of masses M1 and M2. So any translational motion can be described using translational Newton's second law. So we'll use translational Newton's second law, right? So we start from the fundamental stuff, right? And then pulley, pure rotational motion. We have rotational Newton's second law, universal law, which is capable of describing any rotational motion in the universe, right? So we just apply two Newton's laws, right? Translational Newton's second law will be applied twice, right? For M1 and M2. Okay, so basically that's the general strategic approach of to this problem, right? And now let's start doing this. So whenever you apply Newton's second law, first step that we have to make, preparation, right? So we need to choose coordinate system and identify all forces acting on objects, right? And then we can start applying Newton's second law. Okay, so let's do it. Coordinate system, I will pick different for different objects. For this one, well, you know what? Before I start applying Newton's second, before I start introducing coordinate system, you know what? I can guess what will be direction of acceleration, right? Since numbers are given. If numbers are not given, I can assume a certain direction, right? It's not a big deal. So, kind of, I have a gut feeling that acceleration is going to be this way, right? A. And this will accelerate that way, right? So that's what we need to find. Now, as a result, can you tell me, what should I pick as my y-axis for this mass? What's the direction? Of course, downward. Because, yeah, we usually keep track of pluses and minuses next to forces, but accelerations, right? Chances of mistakes are huge, right? So I will pick my y-axis downward for this. And for that mass, y-axis, I will pick a different y-axis, will be upward, right? It's not a crime to introduce different coordinate systems for different objects, right? They will be connected to the absolute value of A and tensions. And this will be my y for this. For the pulley, of course, we're going to deal with torques. We just need to show the positive direction for a torque. Counterclockwise, we'll follow that convention, right? So, plus tau, CCW direction. Okay, so now we have all the directions. Now let's identify all the forces. Okay, I'm not asking you about these forces because we've done it so many times. Obviously, gravity, M1G. Then, tension along the cord away from the object. T. Tension over here and tension over there, are they going to be different? Yes, because now pulley is not massless. We need to spend some efforts in order to create rotational motion in the pulley. So as a result, force over here and force over there, tension, must be different. If they're the same, of course, you wouldn't be able to create rotational motion. All right, so T. And of course, since the cord is massless, tension within this part of the cord will be the same, right? Within this part of the cord between M1 and the pulley is the same. So I can put, subscript 1. I think I use subscript 1 on this side. Let me check it. Yeah. T1, that acts on the mass M1. This T1 acts on the pulley, right? Okay, on that side, similar situation. But now, of course, I will use T sub 2 and T sub 2. And of course, force of gravity. M2G. Have I missed anything? I think it's a complete picture, right? So now everything is in front of us. Now we just need to grab those Newton's second laws and start applying them. Let me freeze this. Maybe I want to touch it here. Actually, yeah, that's work. Let's rub it. You know, like there was a professor at MIT, Walter Lewin. Have you watched his videos?
Yeah.
You remember sometimes he would go to the class with a banana, right, attached to his shirt, right, some fake banana or some other funky stuff, right? So that's what I feel having this. Okay, so I will start with, yeah, so we have translational plus rotational, translational plus rotational motion. So basically that is the major point of this problem, that we combine two motions at the same time for the same system. Combination of translational and rotational motion. Okay, so I will start with M1. Right, sum of all forces acting on object 1 equals to M1 times acceleration. Right, so universal law. And let's write explicitly. Y direction is in front of us. So gravity is obviously positive, right? Gravitational force positive, tension is negative. So it will be M1G minus T1. Don't include this force. Don't even think. This force acts on the pulley. We are writing down all forces acting on this mass, right? I don't see that often, but occasionally it happens. But not very rare. All right, and it is equal to mass times acceleration. Accelerations are the same on both sides, right? Because they're basically like rigidly connected. Cord is under tension. Right, so equation number 1. How many unknowns? Tension, acceleration, 2 unknowns. We need more equations. So we'll start piling lots of equations. So now M2. Right, okay, so I will start writing immediately. Right, so M2A. Now you see y-axis is upward. I pick this way. So now my tension is positive, gravity negative. T2 minus M2G equals to M2A. Equation number 2. How many unknowns now? Overall in 2 equations, T1, T2, acceleration. 3 equations, 2 unknowns, still not enough. Let's keep dumping equations, right? Adding. So now pulley. Now rotational Newton's second law, because this pulley doesn't experience any translational motions, only rotational. And we're going to use this simpler form, tau equals II. Yeah, of course you can use that, but there's no point. Since moment of inertia doesn't change of the pulley, so we can use that. Right, so sum of the torques equals moment of inertia times angular acceleration. So far so good. We've done these problems in our recitation classes, right? So I'm not asking you much because we've used Newton's second law so many times, right? So I'm not asking you many questions. Okay, torques. Torque produced by this tension, right? And torque produced by that tension. There are only two forces which produces non-zero torque, T1 and torque T2. You see, on purpose I left gaps. You know why, right? Let's identify signs. First, torque produced by T1, positive or negative? Positive, right? Because again, axis of rotation over here, that's our positive direction. If a force tries to rotate object in a counterclockwise direction, that torque is positive. Again, I keep adding tries because in this case, yeah, actually actual rotation will be that way. But quite often forces, they fight with each other, trying to rotate objects in different directions, right? And who is going to win, who knows, right? So that's why every time I keep adding tries. So positive, let me put plus in front. And this torque, again, relative to this axis of rotation, this force tries to rotate object in this direction, which is clockwise, which is our negative direction, right? So I will put minus in front. Okay, and now let's complete this equation. So it is equal to moment of inertia times angular acceleration. So equation number 3. So now let's count number of unknowns and number of the equations. Okay, now I'll start circling them. So T1 is unknown, acceleration is unknown, T2. What else is unknown? Actually, we didn't dive into this, but we will see that there are no unknowns over there. Right, okay. Angular acceleration is another unknown. So we have 1, 2, 3, 4 unknowns, 3 equations. Again, not a complete system. What else do we have to add in order to complete this system? Quite often students forget about this equation, right? But it's one of the essential equations which allows us to connect, link rotational motion and translational motion. Which equation I'm talking about? Huh? No, dive deeper. You remember 3 levels of kinematics, right? Position, velocity, acceleration. What is deeper than velocity? Acceleration.
Acceleration equals
yeah.
velocity.
Tangential or linear acceleration equals angular accelerations times radius, right? Okay, linking equation. Of course, this equation is given in the formula sheet in the set of equations which connects rotational motion and translational motion and rotational motion. Right, okay, so usually I just call it a linking equation. You can call it somehow else. So A equals to alpha times R. Basically, okay, if you're confused, what's the logic of this equation? This acceleration of this mass m1 and a tangential acceleration of this point on the edge of the pulley, are they the same? Of course the same, because there is no slipping between the rope cord and the pulley, right? There is no slipping. So this tangential acceleration and this linear velocity accelerations are the same. And then we know how to connect tangential acceleration with angular acceleration. That, right? Okay, so that's the logic behind this. No, it's very often it's called a no slipping condition. Okay, and now we did not add any additional unknowns, so now we have 4 equations and 4 unknowns. Now finally it's a complete system. Lots of equations, but at your level you should be able to handle this system. Okay, so let me write. So this is equation number 4, and again I already circled these unknowns. Right. So 4 equations, 4 unknowns. Okay, let me write underneath the line. So 4 equations plus 4 unknowns So the rest is algebra. No, come on, if algebra left, physics is over, right? So that's the happy moment, right? Okay, so let's just quickly okay, any questions about the physics? Basically, again, the major point, combination of translational and rotational motion in this system like this. Okay, good? Okay, now let's solve it. Usually you just get alpha from the equation number 4, plug it into this equation to reduce to 3 equations, right? So let's get from here. Right. So from 4, we'll get alpha equals A over R, and we will plug it into the equation number 3. You know what? No, you know what? Let's dive into torques. Okay, I realize that we need to dive into torques. Physics is not over, not yet. We did not calculate torques, although in this case it's quite simple. Right? So I need to change the happy face to back to sad face. Right. So torque, can you still see it? Okay, good. Table is lower, right? Because I remember before I had to stop at this point and move to somewhere else. Okay, torque by T1. Do you have troubles calculating these torques? You can use either of these formulas, right? They're all easy. What's the angle theta for this torque? Okay, let me write explicitly. So it's R T1 and sine of which angle? What's the angle? 90 degrees, right? So force T1 straight down. What is R? From the axis of rotation to the point where the force is applied. So this, okay, R equals to R capital, right? So this is our R, T, and the angle between them is 90 degrees. So torque produced by tension over the pulley is probably the easiest torque. Just radius times the value of the tension force. Okay, sine of 90 degrees. Sine of 90 degrees is 1. So it will be just RT1. Oops. So what will be the value of the torque RT? Torque produced by T2, R times T2. Similar. Torque produced by T2 will be, of course, R times T2. Okay, now let me rewrite equation number 3. Right, let me rewrite equation number 3. Right, so equation number 3. Where is it? Here. So it will be, I will factor out R immediately, so I'll have, maybe let me do it step by step. RT1 minus RT2 equals 2. And instead of alpha, I will plug this. A over R. Right. Again, how are you going to solve this system? It's up to you, right? Usually, now I will take T1 from the equation number 1, T2 from the equation number 2, and plug it into this equation. As a result, we'll have only one unknown left, right? So let's do it. So equation number 1, T1 will be equal, it goes to this side with plus, this goes to that side with minus, so it will be M1 G minus M1 A. So you see, T goes to this side, this term goes to that side with minus. Right? Okay, now equation number 2, I will do the same. Actually now, equation number 2. Yeah, it stays there. T2 equals to M2A. This term goes to that side with plus, M2G. Right, so now this goes instead of that, and this goes instead of that. And as a result, we'll have one equation with one unknown A. At this point, you shouldn't be having significant issues, troubles with solving systems like that. Although, yeah, still I can see occasionally you do have. Okay, so now, okay, I will continue this equation. I will take these two R this and R that, and put it here. Right. So as a result, I'll have T1 minus T2. T1 M1G minus M1A, so it's the T1. Then minus T2, it's that M2A plus M2G. And these R's, I'm going to bring them here in the denominator. I A over R squared. Okay, so now finally one equation, one unknown. So we just need to solve it for A. So A is here, A is there. Wait, A is here also. I've got 2 places only left. Where should I take them? Okay, this goes to that side with plus, this goes to that side with plus also. I will arrange that way. So then as a result, it will be M1G minus this M2G. It's a little bit tedious in terms of algebra, right? And this will be with plus M1A plus M2A plus I A over R squared. Okay, A gets factored out. And what is in the brackets will go over here. So as a result, finally, acceleration equals M1 minus M2G divided. I factor out G on that side, left hand side. And bless you, right? So M1 plus M2 plus I over R squared. Whew. Finally, numbers. Okay, I'm not going to plug numbers, no way. Actually, I didn't. So, no numbers. You can plug numbers. So, that's the answer. What will be acceleration if mass m1 equals to mass m2? From the everyday experience. If masses are the same, acceleration, 0. If m1 equals to m2, acceleration 0. And whenever you see if you have some subtraction in the denominator, chances that you screwed up somewhere are very, very high. Because if there's a subtraction in the denominator, infinity is possible. You can get 0 right under certain conditions. Okay, yeah.
Would that inertia, moment of inertia, be equal to mr squared, or is that going to be?
No, in this case, it's a disk basically. It's 1 over 2 mr squared. Right. Actually, I can write it down. No, it's mr squared. Okay, sorry, I haven't used it for some time. So yeah, 5 over disk mr squared. Yeah. But of course, as I said, all the time, these will be given. Right? This will be given. Anything else? Okay, yeah.
What's the value of R?
Say it again.
What would be the value of R if you were to work itself?
Value of R, you don't need value of R.
So,
Okay, it can be anything, right? 5 meters to 5 centimeters, right? I like 5 number, right? Because when I was in high school, 5 was the highest score, right? So on the test, so since then it's a subconscious love of number 5. Anything, but in this case, you see, mr squared, this r squared and that r squared gets cancelled all the time, right? So in this case, it doesn't sensitive to the value of r. Anything else? Okay. Okay, now the fun stuff, the new stuff. So we played with moment of inertia, cross product, torques, angular momentum, and now a little bit of rotational Newton's second law. So now static equilibrium. It's a new stuff, right? And you don't have much time to practice that, right? We just introduced that, right? So, couple of problems about static equilibrium.
Ja kindlaks tegid ka, no mida teha, kui see silmas ennast parandaks. Nii tegid paberid ja jahipäevi just siit ha. Ma tean ju
Okay, let me label it as beam stability.
Still, it was funny that this is called, we just keep calling it that.
Okay, it's difficult to describe, I will just draw it, right? The system. So let's assume that this is a wall. Then, beam, in our recitation classes we have horizontal beam. Now let's tilt it. So let's assume beam is, okay, let me make it bigger. Beam is like that. So that's the beam. Okay, then we will use a rope. So this is the rope which is connected to the wall. Then, what else? Yeah. And now, let's say from here, we'll attach another rope and we'll position here a sign. Let me write something. Example. And what else? Yeah, that's it. Now some numbers are given. Numbers. Okay, I will use probably blue in order to show those numbers. So this distance, all right, between the point where the beam touches the wall, basically that's where the hinge is. This h is 3.8 meters. Then angle, this angle is given. Theta is 37 degrees. Okay, so now masses are given. Okay, I am tired with the amount of 12 kilograms. All right, so yeah, m equals m equals to 12 kilograms. My sign. Then, no, hold it. Uniform beam. No, it's a beam has 12 kilograms. Yeah. Okay, it's M capital. M capital, it's that beam. Right. This is M small, and M small is 21.5 kilograms. And the length of the beam, L, over here, L is 7.2 meters. Right. Yeah, and maybe I will write the angle also. So theta is 37 degrees. Right now, I cannot tell exactly what needs to be found because again, we need to first identify forces. And we will have to find definitely the tension in the core. Right. Okay, so what? It's a stable equilibrium, static equilibrium. We need to satisfy these three conditions. So let me write them down over here. Right. Sum of the forces in the x direction equals 0. Right. So then sum of the forces in the y direction equals 0, and the third one, sum of the torques equals 0. What are the origins of these three equations? Where did we get them? Newton's second law, right? It's just basically Newton's second law with zero acceleration. So whenever we use Newton's second law, every time we start again with the coordinate system, identifying all the forces, and then we'll start using Newton's second law. So the same story is here, right? So nothing new except for we'll need to arrange everything properly, right? But all these ingredients, you're familiar with all these ingredients. Okay, so coordinate systems. Let me, where did I do it? Okay, I found this space. Right? So y, x. In this case, the origin is not that important where you're going to position, because since we want to find just forces. Then, for torques, this will be our positive direction for a torque. Of course, it's a c squared, CCW, right? Okay, so now all directions are given, and now let's identify forces. Okay, the most important part. Let me extend this one. Let's start from this point, from the top of the beam. You know what? First of all, which object are we actually trying to stabilize? The beam. Remember that we're not stabilizing the sign. Sign, it's very easy, stabilization of the sign. Force of gravity, tension in the opposite direction, it's easy to calculate everything. We are stabilizing the beam. Right. So we need to draw all forces acting on the beam only, nothing else. Right. Okay, so on the beam, over here, yeah, of course there will be mg acting on this sign. And what will be the value of the tension in this cord? The value of the tension in the cord will be equal to the weight of the sign, right? The weight of the sign. Okay, let me draw it like this. So it's which way I label it? Just a second. I label it as T1. And of course it is equal to just mg. This mg, right? Okay, so that's the first force. Then, what's next? This roll interacts with our beam, giving us another tension force. I will label it as T, just T. Next, where?
Who would
So,
you like to call?
what? Who? Come on, at this late, right? You can scare her after a long day of work. Right. I'm not losing my sanity, it's good, right? Right. Okay, so next. Beam has weight. Where should we draw our gravitational force acting on the beam? Center of mass. Right, we're going to use the beauty of the center of mass, another beauty of the center of mass. Right, so since it's just a beam, so the center of mass is at the center. Right, so let me just draw it. It will be M capital G. You see, I started from the top and just moved down, identifying all the forces. Now we are at the very bottom. So, forces. First of all, which force, any of the forces acting on the beam right now? At this point, not right now, at this point. Normal force, right, because interaction with this flat surface, right, so it gives us normal force. Let me look how I label this. Okay, first of all, I label this point as A, and I'm going to call this force as F-A-H. A because it's a point, A, H horizontal. You can come up with your own notations, right? Horizontal. H stands for horizontal. A because it's a point A. Yeah, of course, the nature of this force is just a normal force. It's just a normal force. The nature. You can use N if you like to denote this force, because it's just a regular normal nature. Regular normal force. What else?
Friction.
Of course, which friction? Static, right? Because we're trying to achieve the stability, right? So nothing moves, right? We don't want to have here kinetic friction. And that force is going to be, right? Because again, it tries to slide down, but of course static friction force will prevent from that. So I'm going to label it as FAV, I think, yeah. Right, so let me label it as FAV. Wait, wrong place for the vector sign. Right, and. Yep. So almost preliminary steps completed, except for, I kept bugging my students in my recitation classes, right? Now, the final step in terms of preparations, what else do we have to identify? What else do we have to show?
Point, rotating.
Axis of rotation. In order to work with, in order to balance, work with torques, in order to balance torques, we need to make a decision which axis of rotation, okay, imaginary this axis of rotation we're going to use, right? And we have a freedom, right? The choice of an axis is arbitrary, but we have to make a decision, right, about that axis of rotation. So, which axis of rotation is the best? So if you have a freedom to choose any axis of rotation, of course you need to use it in order to reduce the amount of work that you have to do, right? So which axis of rotation is the best? The smartest. Right. What?
Point A.
Point A. If you pick this point, torque produced by this tension will be zero. Only one torque will be zero. If you pick this point, torque produced by this force will be zero. Again, only one torque. If you pick, for example, somewhere over here, none of the torques will be zero. If you pick this point, this torque will be zero. But of course, if you position over there, two torques will be zero immediately, right? Because force goes through the axis of rotation. Of course, point A is the best. Okay, let me show that. Axis of rotation at point A. Right. Okay. Now I can erase this. Okay, so now you can start with any of these equations. In order to create a nice flow of the solution, right, sometimes it's better to start with this equation, then continue with that equation, then with this, right? So on the exam, of course, I will try to guide you. I will tell you, balance this to find that, balance that to find this in part B. So in order to have a nice flow of your solution, right? Okay, so in this case, I will just look at my notes in order to follow my nice flow. I will start with balancing all torques. Actually, this is the hardest part usually. So let's, equation number 3, let's balance torques. All right, so sum of the torques equals to 0. And again, my piece of advice again, start from one end of the beam and start moving, counting all the torques. Don't move randomly around. You can miss one or more forces, right? Okay, I will start with which, it doesn't matter, right? Let me start with, okay, the bottom. I like to dump torques, I will start from here. Torque produced by H plus torque produced by the force AB. Then, torque produced by M capital G. That torque, is that torque positive or negative? Negative? Again, look, we decided to use this point as our axis of rotation. So imagine rotationing this rod about this point. So this force, relative to this axis of rotation, tries to rotate the beam that way, down, right? Which is our negative direction. It's a clockwise direction. Again, you need to understand that there is no way, there wouldn't be any rotation over here, right? We're balancing torques, but each of the forces tries to rotate. Think about this tries all the time. So of course, torque produced by this is negative, right? So I will put minus. Okay. Now next, this tension. Tension produced by T, positive, negative? Positive, right? Because again, now that force tries to rotate in the counterclockwise direction. Again, assuming that the axle is at the point A. Right, so plus. And obviously this torque produces negative. And at the end, don't forget to write 0. Because it looks usually strange, like a big-headed equation, right? Without the left-hand side, oh, right-hand side in this case. Right, so this is 0, this is 0 because of our smart choice of the axis of rotation. And now let's start taking care of each of these torques underneath separately. Right, so torque produced by M capital G. Three options. You can use either of that, either of those. I wouldn't go with this. Actually, I could easily do that, right? But I wouldn't recommend. Which better to use, this or that? F perpendicular times R or R perpendicular times F? For me, it's better to use that. Let's try to understand what is what. If I draw line of force, this is my line of force, which basically line which goes through the force. Here, line goes through this force. And then R perpendicular, it's the shortest or perpendicular distance from the axis of rotation to that line of force. Right? So now R perpendicular will be, okay, I will draw it underneath. So this R perpendicular from the axis of rotation to the line of force. Okay, I drew it underneath. Of course, it should be over here, but it's the same, right? Okay. So now, how can we find this? You know what, let me label, I will give you some points maybe. I mean, here, label some points. Let's call this point, this C, this, for example, I know B point. So basically, we just need to find this distance AB, right? That's our R perpendicular. What's the value of AB? Let me write first, it's R perpendicular times M times G. And now I will open my explanation box. R perpendicular is AB. How can we find that? Geometry. Look at this triangle. A, C, B. Let me draw. Write. A, C, B. So now, from that, by looking at that triangle, what's the value of AB? What's the value of the hypotenuse?
L.
L over 2. The total length is L. This point, this force goes through the center of mass point. You see? It's a midpoint of the beam. So this AC, hypotenuse of this triangle, it's a L over 2. This is L over 2. What's the value of this angle? You see this angle. What's the value of that angle?
37.
37 degrees. By construction, this angle and that angles are the same. So now, what's the value of, how can you find AB? L over 2 times cosine of that angle theta, right? Geometry. Okay, so now as a result, AB equals 2AC times, what did I say? Cosine. Yeah. Cosine of theta. Okay, and I can, you know what, I will go underneath. No, I will continue. L over 2 cosine of theta. My explanation box, where I show what I do in order to move from this point to the next point. Right, so as a result, the value of this torque, L over 2 mg times cosine of the angle which is given. Every time in the problems like this, draw a line which goes through the force, which is called line of force, and then see what's the shortest perpendicular distance between the axis of rotation and that line of force. Right. The same trick we used to calculate angular momentum of point mass. You remember our perpendicular times p there. Now it's a times f. Make sure that for the exam you're comfortable with finding these, finding torques using these ideas, right? Because I can guarantee that there will be something similar to that. Okay. Looks like you're not laughing anymore. Back to being scared, right? All right. No, it's not that bad. It's just a question of practice. Right? And again, if you struggle, you can come to me or our recitation instructor as well. Okay, so got this? Did you understand? Okay, so now let's move on. Let me check. All right. Yeah. So now next what? This torque produced by tension. Let's use the same idea. R perpendicular times force. R perpendicular times T. Okay, now I'm not going to move before you tell me what's the value of R perpendicular. What's the value of R perpendicular? Huh? Okay. Again, look. How did we find R perpendicular for this force? I drew the line of force. Draw the line of force which goes through our force now. Our force is T, right? If you draw a line of force, it's this line. Now, you see that line? What is perpendicular distance, or the shortest distance between our axis of rotation and that line?
H.
H? Is he right, or he's just trying to make our life harder? H?
Yes.
Yes, H. Use all the time this trick, right? Draw a line of force, line which goes through your force, and then see, okay, this is the line and this is our axis of rotation. Just to find the shortest distance, perpendicular distance between the point and the line. You all can do that. And most of the time it's just in front of you in the picture. Right? That's the trick. Okay, so, okay, now let me label this triangle so that you can at home identify it. So this is point A. Let me call this point what? for example, D. D, and this point, I'm running out of
E.
what? P?
E.
B, I have B.
E. E.
As an elephant. E.
Never thought about using E. Okay, so now let me open this explanation box. So triangle ADE. ADE. So from that triangle, basically, right? Okay, so you see that in this case, our perpendicular, too big. Our perpendicular is just H. Right? So it will be H times T. Wow, it's so simple. Yeah. I even doubted myself. H times T. Whew. What's next? 0, done. So T1, torque produced by T1. This is usually the hardest part of the problems like this. T1. But again, if you know the idea, it's just a bunch of mechanical works, right? T1. Whew. Okay, I see what can be done. So in this case, let's use the same. Our perpendicular times now T1. What's the value of our perpendicular now? Again, draw the line which goes through that force. In this case, T1, right? So that is our line of force. And what is our perpendicular in this case?
C.
C? Okay, since it's not labeled, right, you have troubles. But maybe in terms of a expression, formula, how can we find that?
L cosine 37.
L times cosine of 37, right? So let me now label these points. So let me extend this line. So let me label this point. What's the name for this point? F. Okay, so now triangle AM. No, okay, yeah, no, it's not point M. It's a mass M, right? Okay, now I'm not giving you freedom of choosing. I want to use K. You're giving me some strange names, right? Alright, so I'll open my triangle. Open the explanation box. Triangle AKF. Okay, and now for everyone, if you still don't see, our perpendicular now. So this is axis of rotation. That is the line of force. And this AF is our perpendicular in this case. Right? So in this case, our perpendicular is AF. And from the triangle which I just told you, so the total, the hypotenuse, the length of our hypotenuse is L. This angle 37, L times cosine gives us this adjacent side. Right, so it will be, where I am, here. So it will be L times cosine of theta. And I can close my explanation box. Good, that is the last torque. And after that, balancing forces are way easier. So L cosine theta T1, or I will write L T1 times cosine theta. Okay, so now I can separate this. And now let's put all these torques finally back to our equation. Right, this. Okay, and I will show that now. I'm going to write this explicitly. So minus this minus L over 2 mg cosine theta minus this is this torque. Now torque produced by the plus ht. Then this negative minus L. Actually, T1 we know, right? T1 equals to mg. So let me plug mg instead of T1 immediately, right? Can I?
Yep.
I think you should be able to see. So L mg times cosine of theta, and it is equal to 0. Actually, it looks kind of longer because I'm trying to show all the triangles. But if you by yourself, right, you can look at the picture, and if you see that are perpendicular, you can use it, and of course we will find it. So it's actually much faster than it looks now. Right. How many unknowns do we have? Given. 1. Right? All these L's are given, angles are given, masses are given, H is given, everything is given. So we can solve it for T. So from here I can get that tension is equal to 1 over H, and I will just combine. This term goes to that side, and this goes to that side. So it will be mgl cosine of theta plus L over 2 and capital G cosine theta. You can factor out a bunch of terms, a bunch of factors. So it will be gl cosine theta over H, and it will be m plus m over 2. That's it. Yep. Okay, so if you plug, you will end up with approximately 410 newtons. So the rest of the problem is much easier. Now, once we balanced all the torques, these two conditions usually the easiest, right? So now condition number 1. Have I tried condition number 1? Next one. Yeah. Sum of the forces in the x direction are 0. So again, start from somewhere from the bottom, right, and move to the top. First, force AH. Well, I mean AH. What? Something like that?
What does it say in the second line? 1 over H?
H.
Oh, above that.
This H. Oops, still.
It's 1 over L.
Better? This is 1. Yeah, it's 1. Yeah, it's 1. I haven't factored out L yet. Okay, so now all forces and x component, all forces in the x direction and x components of all forces. It doesn't matter where those forces act on the beam, right? As long as they act on the beam and they are in the x direction. So FAH, full in the x direction, and it's a positive x direction. So it goes into the equation with plus. So plus FAH. All right. Then nothing from here, nothing from there, nothing from here. These fully horizontal. And tension T acts in the negative x direction. So it goes into the equation with minus T, and that's it. There are no any more forces in the horizontal direction. So it is equal to 0. Tension we just found, so we can find horizontal force acting at the hinge. So from here, it will be FAH, AH equals to T equals to 410 newtons. And the last condition we need to balance forces in the y direction. Okay, there are more forces in this direction. This AB positive because it acts in the positive y direction. This mg negative because it acts in the negative y direction. And this T1 negative because again it acts in the negative y direction. So we need to combine all those forces and they should give us 0. Right. So it will be FAB M minus M capital G then what else? Minus M minus T1 which is mg minus mg equals to 0. Right? I think I didn't miss any forces. Again, all this given, we can find force in the vertical direction acting on each. FAB equals to M capital plus M small times G. Where are my notes? What's the value? 328. 328 newtons. Again, balancing forces usually trivial, but you need to, of course, show a free body diagram. Balancing torques requires some practice. Right. So how do you feel? Yeah, first, before your feelings, right? So about his feelings, let's talk, right? Yeah.
So, was the purpose of this just to find those three variables?
Forces, right? Those three forces, right? We know that this system is stable equilibrium, right? We use those facts in order to find what is unknown, right, in the problem, right? Yeah. Yeah.
I was like, if there was like a person like on that like beam, would you just say the weight force?
If you hang a person over there,
Yeah, like a person who's like
it's a nice application of this problem, right? Instead of a side.
walking up the beam.
It's what?
What?
He was walking up the beam.
Just like
Can you just again repeat?
Like it's a ladder. Like let's say there's a ladder.
Yeah.
And like when you say the a point mass, would you just use the weight force, like the?
Okay, I'm still trying to understand. Okay, let me draw it over there, all right, in order to, because actually my next problem, I've been standing and thinking, should I start solving it or not? Okay, are you talking about this? So let's assume that you have a ladder, right? So here's the wall, here's the, floor and the wall. I'm back to my topic, right, in my recitation classes. So you're saying, what if we have here persons?
Yeah.
Okay, awesome. So, of course, that person has a weight, right? And with that weight, this guy will be acting on the ladder. And so what's the direction of that force? Since the ladder is designed in a normal way so that steps are horizontal, right? So you're basically standing straight, right? So that force which you apply on the ladder goes straight down. So you're going to have this force. Right, so it will be, okay, let's assume that his mass is m, mg. So that will be the force acting on the beam, or on the ladder, right? Actually, it's from the next problem which I wanted to, first I wanted to discuss your feelings, right? And then, in order to make a decision, right? Should we go into that business, right? Can you read minds? No?
No.
Because you basically just jump ahead of me slightly, right? You asked something, right?
You answered it.
You answered. Okay, good.
Oh, I actually can.
Huh?
Gave me an A.
Yeah. All right. For mind reading abilities. Okay. So let's continue. Okay, again, it's up to you. You can go, right, you can stay. The record so far, we had like 4.5 hours, right, 1 year, right? But we started earlier. Right? Because, it was a couple of years ago. Exam review, not the exam. Right. Yeah. Just a second, can you... Okay, we need to start it over again.
Torque on the fork. That's torque AH and torque AB. How are they zero? How are they zero?
Why are they zero? Okay. Door is far away, right? But you can easily imagine, right? So let's say you want to open the door. You basically, you have to create a torque in order to create rotational motion. Opening the door is a rotational motion. And if you go and start applying your force at the hinge, will you be able to create rotational motion? No, you wouldn't be able to open the door, right? Because your torque will be zero. Because you apply your force at the axis of rotation. The lever arm is zero, right? But if you slightly move away from the hinge, yeah, you will start creating some torque, but it will be very, very painful to do that, right? Because you have to apply lots of force, right? But you can balance it by creating longer lever arm, and then you have to apply less force. Right? Okay, anything else? You know what? Let me postpone this ladder problem to, okay, at the end, let me solve this easier. All right. Basically, here we'll have to juggle with Newton's second law and, actually no, let me first state the problem and then we'll start discussing. I know you're also tired, I'm also getting, actually I'm getting excited. Okay, can I start erasing? This problem is easy. So we have some solid disk, which is capable of spinning around the axis of rotation. Okay, solid disk, uniform, not like that. And mass is given, radius is given, right? And let's assume that we apply non-stop, constantly, force tangential, along the tangential direction. Non-stop, we're applying force. We need to find a few things. First of all, we need to find acceleration, and then we need to find the, if we assume that we start from rest, what will be the final angular velocity after, let's say, a few seconds? Right. Why I want to discuss, because although these problems are very similar to the translational motion, but for whatever reason, students usually, whenever they see rotational motion, you guys start panicking, right? And it's lots of strange things, right? You can see on the exam papers, right? So that's why I wanted to discuss that. So let's erase this and. And then at the end, if you still feel good, we will go finally into the ladder problem with the person standing, right? Okay, so I will just put a new bullet, new problem. So we have some kind of disk. All right, so what is given? Mass 4K, radius 0.18 meters. Then steady force is applied. A steady force. Okay, tangential. And let's say force is, even here I picked the numbers. I told you I like number 5. 5 newtons force. Yeah.
What is R?
0.18. Okay, I'm thinking which part should Which part confused you?
No, I just didn't.
Ah, okay. Yeah, that's why the red shouldn't be used as the major color. Okay, let me switch back. Not enough contrast. It's nice for decorations of the on the whiteboard, but not for the major color. So I will switch back to red. Right. It's been a rough week. 5 minutes. I'm sure that you are speaking also.
Chernobyl.
Right. We're going to have rotational motion. Which parameter do I have to give you? Moment of inertia. Mass is not enough, right? So I need to give you a formula. So for this, in this case, moment of inertia is 1/2 mr squared. mr squared. Right. Okay. So let me sketch quickly. So this is my disk, radius r, mass m, and the force acting tangentially. So this is my force F. And of course, axle is over here, right? So that's where axle is. Again, so let's start with the global picture. We want to find an acceleration, angular acceleration, right? So we need to find angular acceleration. Rotational motion, right? Which fundamental law can be used to describe any possible rotational motion? It's the easiest approach, right? Just grab and start using, and maybe something will fall out of it, right? Rotational Newton second. Since moment of inertia doesn't change its value, so we'll just go with I alpha. All right, so rotational Newton second. So net torque equals moment of inertia times angular acceleration. Since there's only one force, I'll skip vector signs. And if we have a few torques, then we'll have to take care of it. So, moment of inertia is basically given, right? So we just need to find torque. So torque produced by my force F. What will be the value of the force? I mean, the expression for the torque. In this case, you can use any of these tools and they're equally easy, right? You can use this. R basically it's a radius and angle is 90 degrees, right? So in this case, you can use one, right? So R, T, no, it's F. F and sine of 90 degrees, right? And R, it's R capital, right? So it's now R capital, so it will be R times F. Right. Okay, so now just basically we can plug it into that. So RF equals to I alpha. So it's basically one line, no, okay, two line problem. So now no troubles. You shouldn't have any troubles. Although quite often I give problems like this and the results are not very impressive. Every time, yeah, seriously. Although idea is like for translational motion, but whenever students see rotational motion, it's so alpha equals to RF divided by moment of inertia. Right. Moment of inertia is given. Right. I still don't know why I used M capital, right? I cannot explain. Because usually all the time we have some disk and there's some objects and the disk is mass M capital. It's M small in this case, sorry. I have no idea why I picked M capital. Right, so Rf and 1/2 m r squared. So 1r gets cancelled, and we will have 2f divided by m. F is 5, m is 4, so it will be 2 times 5 divided by 4. Okay, it's up to 2.
Don't you still multiply by the
They're,
Huh?
they're missing R in the denominator.
Oh, okay. All right, R downstairs, right? Yeah. Atwood is okay. So now I'm not I'm not calculating, right? I'm just writing down the answer. It will be approximately 13.9 radians per second. 13.9 radians per second.
Is that all we?
All the time, if you use normal units out of the rotational Newton second law, alpha must appear in radians per square second. Or if you want to plug the value of angular acceleration in the rotational Newton second law, alpha must be in radians per square second. Don't use revolutions or whatever units. Okay, so that is part A. Now part B. What's the angular velocity after 5 seconds if initial velocity is 0, angular velocity? So now, what can be used now?
Yeah.
Rotational
Kinematic.
kinematic equations, right? It's like what we've done at the very beginning of the semester, right? First, we would apply translational Newton second law to find acceleration. Once you know acceleration, and if that acceleration were constant, we would go and use our translational kinematic equations, normal kinematic equations. Here, the same thing, but every time you have to add rotational rotation. But idea, philosophy is the same. So, which equation can be used or should be used? Since time is given, initial velocity is given, so obviously we need to use the first one for the angular velocity. Right? So, kinematic equations. Okay, rotational kinematic equations. Rotational kinematic equations.
Yeah.
So, omega at 4 seconds equals to omega 0 plus alpha t. And t is given. It asks what's the angular velocity after 4 seconds, assuming that we start from rest. So this is 0. Right, so it's 13.9 radians per second times 4 seconds. Okay, no way, where are my notes? 55.55. Oh, nice. I like 5, and I have now tons of 5s. 55.55. Wow. God feels my desire right from 5. Giving me plenty. Okay, so in radians per second. You can convert it to revolutions. Oh, yeah. I was saying per square seconds. I remember I tried to keep track of, but I forgot to write it right. Okay. Second to the power of 2. Seconds to the power of 2. If you convert it to RPM, okay. I'm not going to do conversion. I will just write down 530 RPM. We've done it many times. You can do it. Of course, you can play with this. You can give, for example, acceleration and ask to find torques. But again, you just grab a rotational Newton second law, invert it, and solve it for what you need to find. Okay, here you shouldn't have significant issues. So, should we go into the last one, ladder problem? Yes? Where is the person who asked me about the person standing on the ladder?
He wants to take a call.
Ah, okay. Should I wait for him? No, right. Again, yeah, if you feel tired, right, you can go. Because I understand it's getting too late. And, although I know we have classes sometimes very late. Can I start erasing? And this will be a long problem, maybe like 20 minutes it will take, something like that.
Ja kindlaks tegid ka, no mida teha, kui see silmas ennast parandaks. Nii tegid paberid ja jahipaadi just sidha. Ma tean ju mida.
Yeah, the life of a student is a tough life. But you know what? To tell you the truth, when I was a student, I thought when I graduate, life will be easier. No. It didn't get easier. So, a ladder problem. At least in my recitation classes, I thought about discussing one ladder problem, but we ran out of time, so we just discussed only free body diagram. But in your homework, there will be one problem left.
It's going to be quick download like the last one, or is this going to take? Remember how the last video for the last exam, you were able to do it quickly, you could help?
Yeah, this guy, right, Sunny, right here, built me a fast computer. He forced me to buy the fastest CPU. I spent tons of money on that, right? Now I have like a real, like, I don't know, Peugeot, right, in my office. Right? So it can crunch that video like within 3 hours, right?
I guess when are you going to lie?
I have a class tomorrow, so I need to prepare for that. So and then, okay, I will do my best. So by the end of tomorrow, I hope it will be ready, right? So I will do my best because I still have classes. Okay, let's move. The ladder problem with the person standing, not hanging, right? Because first I was. No, just like normal way, right? Don't think some weird stuff, right? Wall. Right. Then wall. Again, I'm doing this floor, ground. Right? Okay, yes, it's been a long day, right? And again, since we have an exam on the first day of the exam week, you have to prepare the exam in advance, and we need to send it for printing, right? So plus finalizing the semester. It's usually the end of the semester. Okay, so now let me draw a ladder. Okay, let me make it a bit bigger. So this. Then. Okay, ladder. Okay, so what is given? So about the ladder. So M capital, no numbers. L length. Then angle theta, that's the angle that ladder makes with the wall. Okay, you know what, before I continue, let me explain the physical situation. Yeah, now I realized I need to draw a guy. So here there is a guy climbing this ladder. Okay, here. You understand why? So, you know, if you keep climbing, right, so first the ladder can be stable. But you can keep climbing, right, and at a certain point, if you don't design it properly, it can start sliding. So let's assume it's that moment when, at this distance from the floor, the ladder is about to start sliding. So next moment, and the ladder starts going right down. So that's why I draw the set face. or terrified of it, right? So it is about to start sliding. So basically this friction force is about to give up. All right? And of course this angle is the minimum angle for stable equilibrium situation. Right? Okay, so now let me write it down. It's about to start sliding. To start sliding. All right, so, okay, so I explained the situation, and actually what do we need to find? Yeah, the most important question, yeah.
What's the first word? I don't know.
It is about to start sliding. Okay, start writing nicely. Still, it is I, nice, elegant letter I.
It's a Y. It's a Y.
I grew up when we did not have computers, so we have to write nicely, right?
Looks like a Y.
Silly. Wrong generation. Different values, right? No, I remember I had a book about calligraphy, so where they would show you how to draw nicely. Okay, it is about to start sliding. Alright, okay. Yeah, then, what else is given? This distance, D. So he managed to climb up the ladder distance D, and now it is about to start sliding. Then, what else? Yeah, and the angle, of course, is given. So what else we have? We have D, angle theta, masses. Mass of the person and mass of the ladder is already there. And we need to answer, of course, the most important question for this person. What is this friction of coefficient of static friction, right? So let's find the coefficient of static friction. Right. So let's find mu s. Of course, in this problem, don't even start thinking about the answer. Strategic approach. We have to balance all. Okay, the system is still in stable equilibrium, right? So we have three conditions which we can use, right? Draw a free body diagram, choose all the directions, write all the equations, and then somehow over there we will start extracting that coefficient of static friction, right? Because right now, no, it's impossible to see how we're going to get it. But somewhere down the line, of course, you will be able to see. Right, so okay, let me write those three conditions. So sum of the forces in the x direction 0, sum of the forces in the y direction equals 0, and sum of the torques equals to 0. And again, I'm not asking you at this moment which point should we take as an axis of rotation, right? Because in order to answer that question, we need to identify all forces acting on the system. Only then we can make our smart choice and choose the best axis. Okay, so let me start with the coordinate system. Y, x. Then for torque, this will be our positive torque in the counterclockwise direction. And all forces. Let me start from the top. Okay, two additional pieces of information. No friction of the wall And of course, there must be a friction in the floor, on the floor, because otherwise you will never be able to stabilize the ladder, right? So of course here with the friction. And coefficient of, we need to find that. So of course with friction. Jesus Christ. With friction. Right, okay, so now free body diagram. Force acting on the ladder from the wall. Normal force. You shouldn't have any troubles, right? So it's like if I lean, there's only one force acting on the normal force from the wall, right? Okay, at this point. Okay, I will label it. Which way I label it? Okay, my standard way. F sub W. W stands for wall. But the nature of this force is just normal. Normal force. The nature of that force. Then, force of gravity acting on the ladder. Where should I draw that force? Center of mass. The beauty of the center of mass. Somewhere at the center, okay, here we have Cm, and I will draw that force okay, M, capital G, mg. Center of mass, Cm. Yeah.
Why is there no friction from the wall?
Blame the author of the problem. Me. Yeah, you can add the friction, but in that case, okay, just add complexity. So usually we can skip that. Just a statement of the problem. Then, yeah, and again, which object are we stabilizing? The beam. Oh, the ladder. The ladder, right? The ladder. So, person acts on the ladder with his weight, and of course it goes straight down. Right? So that is m small g, m small g. And finally, at the bottom, again, normal force. Right? And I will label it again in my weird way, FGY. F sub G Y, but again, the nature of this force is just a regular normal force. The nature. G stands for ground. Why? Because it is in the y direction, vertical direction. Wow, it's so nice, so wise. Feels like a pressure disappeared from a system. Okay, and the friction force, direction of the friction force. Your left, okay, there, your left. I will label it as F ground in the x direction. Yeah. And of course, the nature is just a friction. Okay. You know what? It's a static friction force. What else should I add to this word, static friction force? Important word. Max. It's a maximum possible, because this ladder is about to start sliding. So static friction force is about to give up. Right? Start sliding, it means static friction disappears and kinetic friction appears. It's a maximum possible static friction force. Okay, I will add this. It's a maximum static friction. And as a result, do you remember the expression for the maximum possible static friction force? Mu times the value of the normal force, right? Mm-hmm. And the value of the normal force, it's a gy, fgy. Right. Okay, so now let me write it underneath over here. So fgx equals to mu static times fgy. Okay, and underneath I will write it, so it's fs maximum equals mu s times m. Because usually we're familiar with this form, right? Fs max equals mu s times normal force. But in terms of our notations, this formula looks that way. Okay, somewhere down the solution, we will use that. For now, I just throw it on the plate to remember, right? what else? Okay, so all the forces are here. So now we need to start applying all these conditions. But before we start applying now, I can ask you which axis of rotation is the best. We have a freedom to choose any axis. Okay, let me emphasize again. Any axis. And of course, which point?
Bottom.
The bottom, of course. The smartest option. Which way I label it? Again, probably A. No, whatever reason, P. I have no idea why. Right, so P. And this is top. I will label as B. This as O. Why not? Stop laughing. We're doing serious business. Right. Again, at this point, at the very beginning, it's difficult to see which equation it's better to use first, and then which next one, and so on. Again, as I said, I will guide you on the exam. I will tell you in the statement of the problem. Okay, I will look at my notes. So let's start with the y. Right. Let's see what we're going to get. Right. So first, sum of the forces. Any axis, and finally we will pick point P. Point P. Sum of the forces in the y direction, right? Yeah. Equals to 0. Again, start from the top or from the bottom, right, so that you wouldn't miss any forces. Fw, positive. Fw. Then nothing, nothing, nothing. And Fgx. Okay, only two forces. They have must balance each other out. So, and the force, friction force in the negative x direction. So minus Fgx equals to 0.
Oh, yeah, y direction. The y direction.
Mg. No, let me start from positive. I like starting from positive. F. Wait. No, we need to call it a day after this. F. G. Y. When the professor fails, it makes you happy, right? It's not nice, right? So minus M capital G and minus M small g. You know what I told you in my recitation classes, right? Story when I started teaching this class, right? And I remember in a similar situation, one girl asked me, so why we're not drawing a force? Because on this person there is a normal force acting on the person, right? So why we're not drawing that force in our free body diagram? Because the ladder will apply normal force on the person, right? So why is that force not on the diagram?
Because it applies on the transl.
Yes, because we are drawing all forces acting on the ladder, right? Only, right? We're not trying to stabilize the person. He's, for now, for more or less stable, right? Next moment he will be crashing, right? Right, but it will be next moment. For now, we're just stabilizing the ladder, right? So we need to draw all forces acting on the ladder. And sometimes I see that extra force in the free body diagram on the exam, which is not needed. Okay. 0. All right, so from here, of course, I can write Fgy equals to M capital plus M small times G. Numbers are not given. Awesome. You know, I don't like crunching numbers. I like writing symbols. Masses are given, so basically we found. So that is the normal force acting on the ladder from the floor. Right, I'll try to control what I say, right? F. I think the next one is X. No. Actually, now next one I try to balance torque. Whatever. Right, let's balance torques. Sum of the torques equals 0. Again, about point P. Axis is at P. All right, so let's start. Okay, I will start from the bottom. Again, torques produced by Gy, torque produced by Gx. And of course, where is that lady? Okay, I forgot to ask. There's 0, right? There's 0 because again, yeah, that was it, right? Because again, those forces acting at the axis, on the axis of rotation, of course, they are not capable of producing any torques. Lever arm is 0. Right. So then next step, force torque produced by that force m small g. That torque, positive or negative? Positive or negative? About this point, this force tries to rotate the ladder that way.
Positive.
Positive. In the positive direction, right? Counterclockwise. Now this is the axis of rotation, right? Positive direction. So plus torque produced by mg. Next, m capital G. Obviously the same, right? Positive. In terms of sign, the same. Plus torque produced in capital G. Next. This. Okay, that torque, positive or negative, the last one?
Negative.
Negative, because that force relative to this axis of rotation, of course, tries to rotate that way, clockwise direction, which is our negative direction. So minus torque reduced by, okay, no, let me just write W, and it is equal to 0. Okay, now the hard part. All right, so finding all these torques. Again, let me start one by one. Torque produced by m small g. Again, we have 3 options. I wouldn't recommend to go with the first one, although if you know what you're doing, you can easily get everything what you need. Most likely, I would go again with r perpendicular f. Again, draw a line of force and just see what's the shortest distance from the axis of rotation to the line of force. Line of force for mg small, right? So this is our line of force. And the shortest distance, it's that one, right? So in this case, it's this. Okay, let me label these points again. So it's a P, A, K. So I will use r perpendicular times mg, and I will open my explanation box. Again, triangle A, PK. So what r perpendicular is KP. So what, in terms of what, how can we write these r perpendicular in terms of what is given?
D cosine theta.
D cosine theta, because we need to find the side which is adjacent to the given, to the angle, given angle. So AP is D, this angle theta, cosine theta. So it will be D times cosine theta. Right. So as a result, it will be mgd cosine theta. It's not that bad, right? Once you practice it a few times, it's right. Torque produced by m capital G. Basically the same story, right? But now, of course, line of force, it's this line, which goes through the center of mass. Good? Is everything clear? So now, let me label this point as, okay, I will use your letter E. Right. So now r perpendicular is E, E. So again, it will be r perpendicular times mg. And now triangle, and now I need this point. Center of mass, point C. B, C, A, E, E, C, E, triangle. Right, and our perpendicular in this case, it's a E, E. Now, what's the expression for this R perpendicular?
L over 2.
This is center of mass, so it's a half length of the whole ladder. The whole ladder is L. So this CP is L over 2. Then this angle is theta, so L over 2 cosine of that angle gives us E times E. Right? Triangle is C, P, E. So it will be L over 2 times cosine theta. Again, if you are still not comfortable with properties of a right triangle, at the end of the formula sheet, there is a small triangle with the angle and all the right expressions. Okay, so it will be mgl over 2 times cosine theta. The next one, the last one. Okay, is that clear? You see, we're doing exactly the same every time. Line of force. And then just look at the diagram. Where is that perpendicular distance? And now, torque produced by that normal force Fw. Okay, line of force. Right? And what is our perpendicular? Basically, it's this, right? Which is over here, right? But by construction, it's that OB, basically, right? So the total length of the ladder L times cosine of angle, sine of angle, opposite. Force of habit after using a couple of times cosine, right? R perpendicular times F W. So now triangle BBO. Triangle BBO. So R perpendicular is OB. So which is, yeah, L times sine. L times sine theta. Okay, close explanation box. And so almost done. So it will be L Fw cosine theta. Right? Yeah. So let's just plug them all. And do better than this. Plug them in our equation. Okay, and I will continue this balancing torques over here. So first one positive, it will be mg d cosine theta. Then this positive mg L over 2 cosine theta. Then this negative, just rewriting actually. And the last torque minus L minus LF. Still alive. Fw sine theta equals 0. How many unknowns are there? 1. Everything is given. This is unknown. All right. I didn't write down what needs to be found, but basically Fw and the. Yeah, I did write. It's really bad. All right. So we found this, right? And okay, yeah, that's done. This is done. Right, so let's we balanced forces in the y direction, now x direction. So the last one, forces in the x direction equals 0, right? You definitely call it today after this problem. Yeah, Fw positive, Fw positive, and friction force is in the opposite direction. So Fgx equals to 0. Right? So here, of course, Fgx equals to Fw. Fw we just found, right? And Fgx we can find. And now, so we used up all our conditions. So now, final push. We need to find static equilibrium. Static coefficient of static friction, right? From this, right? So that's the only place where that coefficient is present, right? So let's just extract this. You know that I already submitted the final exam, right? For printing. I cannot change that. That's why you're laughing, right? You can safely laugh. Okay, I'm not that bad. So now Gx equals to mu s times Fgy. So let's see. Fgx we just found. Fgy is there. Right? So both this force and that force found, so we can solve it for mu sub s. Right? So now we just need to combine what we just found. So mu s equals to Fgx over Fgy. Fgx. Oh my god, I have to rewrite all that stuff, right? No way. Fw. And Fgy will be just n plus n over here, right? You can rewrite it. Let me frame it. I can, to be fair, I can. Okay, so you can ask for many things, but again, bottom line, these three conditions, right? Coordinate system, identify all forces, and of course carefully go through the torques, right? But we already have done enough, right? Examples, so that we would feel comfortable with the finding these torques. Okay, if you have any questions, I'm still here.